Hi everyone, this day we will discuss the technique called separation of variables. Separation of variables is a technique for solving differential equations which involve rewriting the equation so that each variable is only on one side of the equation. For a particular differential equation to fit separation of variables, it must be in the form n function of y dy over dx equals m function of x. Otherwise, the equation would not be variable separable. So for this case, we can rewrite it such that n function of y times dy is equal to m function of x dx. Here we have already rewritten the equation so that each variable of the equation is only on one side of the equation. Here, y, the function of y, together with its derivative dy, and is on one side, on the left side, and m function of x with its differential dx is on the other side. And after this, we then have to integrate the differential equation to be able to find its solution. For our first example, we will solve 1 minus x y prime equals y squared using separation of variables. So, the first step is we can rewrite y prime as dy over dx. The next step is to separate the variables. As the name of the technique implies, separation of variables. We need to rewrite the equation so that one variable is on the one side and the other variable is on the other side. So here we can retain dy over y squared, transpose y to the other side, and transpose dx to the other side, and 1 minus x. So here we have y together with its differential dy and x, a function of x, together with its derivative dx. So we have already separated the variables. There are no x on the left side, there are no y's on the right side. Then we proceed with integrating the equation. So integral of dy over y squared and integral of dx over 1 minus x. Okay, so we have here case of simple power rule on the left side and natural logarithm on the other side, on the right side. So we can rewrite this as y to the negative 2 dy over dy, and we can simply integrate it by simple power rule. Y to the negative 2 plus 1 over negative 2 plus 1. We can place c later on the other side. We can combine the c's because it is simply an arbitrary constant. So this one is clearly not a simple power rule, but this is a case of a natural logarithm. If you recall, the derivative of ln of u, where u is a function of x, for instance 1 minus x, this is our u, the derivative of ln of u is 1 over u du over dx, or simply 1 over u du. Okay, so if we, for example, if we integrate, if we derive the function 1 minus x, 1 minus x, if we derive the function ln of 1 minus x, the derivative is 1 over u, 1 minus x, and du, because of what we call the chain rule, du is simply equal to negative 1. Therefore, since integration is simply anti-differentiation, the integral of 1 over u du is equal to ln of u. So here, the integral of 1 over 1 minus x times negative 1 is equal to ln of 1 minus x. But here, we do not have negative 1 so that we can not readily proceed with the integration process. But we can adjust the integrand so that we can have a negative 1 inside the integrand. So how do we do that? We adjust the integrand. I guess you have already taken this in your integral calculus class. We multiply negative 1 inside the integral 1 minus x. However, in order to maintain the expression, we multiply negative 1 outside so that it's just the same as multiplying positive 1. And multiplying positive 1 to an expression never changes that expression, does not change that expression. So here, since we have 1 over u du, we can now proceed with our integration. And that is simply equal to ln of u. But u, once again, is equal to 1 minus x. So since there is a negative 1 here, the right side is simply equal to negative ln of 1 minus x. So we can substitute it here, negative ln of 1 minus x. Now, we could just write plus c here. We can simply write plus c. But since c is an arbitrary constant and it can take any value of any constant value, we can manipulate it so that it is easier for us to simplify the equation later on. And so, rather than just adding plus c, I can write here negative ln of c. Why negative ln of c? Because as you can see, our ln here is negative. It is easier for us to simplify with 2 ln's using 2 natural logarithms using the properties of natural logarithm. Okay, so I will rewrite the equation here. I will apply the laws of the principles of natural logarithm. If you recall, there is a principle for natural logarithm which states that ln of a plus ln of b is equal to ln of a times b. The other laws for principles for natural logarithm is ln of a minus ln of b is equal to ln of a over b. Another one is if you have, for example, ln of a to the power of n, we can rewrite this as n ln of a. So we apply this principle to simplify the expression on the right side. So we have y to the negative 1 over negative 1 equals negative. Let's factor out negative first. We have ln of negative ln of 1 minus x minus plus c. So negative 1 has already been factored out, the negative expression. So we can now proceed with simplifying this one. We have ln of 1 minus x times c. Once again, because ln of A plus ln of B is equal to ln of A times B. That is principle in natural logarithm. So this is equal to negative 1 over y because of the negative 1 in the denominator. And multiplying negative to both sides, we have 1 over y equals the negative cancels, the negative here cancels, the negative here becomes positive as well. So we have ln of c times 1 minus x. And we transpose y to the other side, we have y ln of c times 1 minus x equals to 1, or simply y ln of c times 1 minus x equals 1. So this is our solution to this differential equation using separation of variables. For some of you who might still be wondering about the integral of 1 minus x, why did it become negative ln of 1 minus x, we will review a little of your integral calculus. So the integral of 1 over u du is equal to ln of u. Alright? So for our equation, for our integral, we have 1 minus x dx, or we have integral of 1 over 1 minus x dx, this one. Alright? So one technique is what we call the technique of substitution, where we have u is equal to 1 minus x. Okay? So here, our u is clearly 1 minus x. So that the expression becomes integral of 1 over u du. Okay, so our du over dx would be equal to negative 1, because 1 is the derivative of 1 is 0, and the derivative of negative x is negative 1. We transpose this so that dx would be on the right side. So this becomes dx equals du over negative 1. Okay? Now we go back to our equation, to our integral of 1 over 1 minus x dx. This is the one we have on the right side of our equation. And as you can see, we have here a value of our dx. Okay? We have a value of our dx. And the value of our dx is du over negative 1. So we simply substitute this value to our dx here. We have now integral of 1 over 1 minus x. Our dx is du over negative 1. And the constant rule for constant multiple rule for integration states that if you have a constant inside the integrand, you can simply factor out, you can simply take that constant outside of your integrand. So we have here negative 1, or 1 over negative 1, which is still the same as negative 1, equals 1 over 1 minus x, which is our u, du. And so this is our u, okay, 1 over u du. And 1 over u, the integral of 1 over u du, the rule says, okay, this is our rule. The rule says the integral of 1 over u du is equal to ln of u. So we simply copy negative 1, and this is now equal to ln of u and plus c. That is why we have negative ln of u plus c. on the right side. Because the integrand or negative ln of 1 minus x plus c, because the integral of dx over 1 minus x is negative ln of 1 minus x plus c. Okay. The other technique which we applied previously in solving the equation was adjusting the integrand. Okay, so if this is 1 over 1 minus x dx, how do we adjust the integrand? We know that if this is to resemble 1 over u dx, so if we substitute 1 minus x with u, we know that ru is equal to 1 minus x, and du is equal to negative 1, or sorry, negative 1. So we need a negative 1 in our equation here, because the rule states that integral of ln of u du equals integral of 1 over u du is equal to ln of u. But we can simply proceed with that integration if we have a value for our du. So in this case, our du is equal to negative 1. So in order to be able to integrate this, we need a negative 1 in our integrand. So we multiply negative 1 times negative 1 integral of 1 over u du. We know that this is the same as positive 1. So multiplying an expression with positive 1 does not change that expression. So since this integrand can simply admit a constant or take out from it a constant, we can have negative 1 enter the integrand. So negative 1 over u du, and we have negative 1 on the outside of the integrand. And negative 1 over u du is, we know that this is already, negative 1 over u, our du is negative 1. Okay, so we have now our du expression. We have now our du expression, which is negative, and so this becomes negative ln of u plus c. Okay, so we still get the same answer using two different techniques. Next, we will solve another example. Sin x sin y dx plus cosine x cosine y dy equals 0. The first thing we will do is we divide all terms by sin y cosine x in order for us to be able to apply the log rule for integration. So we divide everything by sine of y cosine of x. So that is, dividing this by sine y cosine x, we have sine y cancelled. So what is left is sine of x divided by cosine of x dx plus cosine of x cancels, and what is left is cosine y sine of y dy equals 0. Take note that in separation of variables, we do not have to transpose this one to the other side, because by then we can transpose it again to the other side, and the sign is the same. So we can just do our integration while having them on the same side. But if you really want, although it's a bit more complicated, you have this transferred to the other side and it becomes negative. But then later on, you can transfer it to the other side and the sign is still positive. So you can operate having everything on the left side. Okay, so The next step is, after we have separated the variables, we have here all x's, we have here all y's, we can proceed with our integration. Okay, if you remember, we can apply here the log rule for integration. Okay, so our u here is equal to cosine x, and here we will be using the process of substitution so that you will be more familiar. And here we have our u is sine of y. And our du over dx here is equal to the derivative of cosine is negative of sine of x, and the derivative du over dx, the derivative of sine y is cosine of y. Transpose so that dx is on the other side, so we have du over negative sine of x equals dx. On the other hand, here we have du over cosine y, transpose this, and dx to the other side. And I mean dy, because it's a function of y. So next we can transpose, we can have our dx, we can substitute this value for our dx here. So we have integral of sine x. Okay. Our cosine x is our u, and dx is du over negative sine x. Okay, du over negative sine of x. And the sine of x cancels, and we can have our negative move to outside of the integral sign. Okay, so we'll try to solve this first. So we have 1 over u du. 1 over u du is ln of u. So we have 1 over u du. The negative can just be placed out of the integral. And 1 over u du, the integral of 1 over u du is ln of u. And we have a negative sign here, so it becomes negative ln of u. Plus, here we can substitute for dy here, du over cosine y. So we have integral of cosine y over sine y. dy is du over cosine y. For which case, cosine y cancels out, and we have integral of 1 over du over sine y. But sine y is equal to u. So I'll just substitute it here so that it becomes clear for you that this is a case of a log rule for integration. So integral of 1 over u du is equal to ln of u equals, instead of just placing here c, I'll place ln of c so that we can simplify much easier later on. Okay, so substitute everything. Our u here on this side is cosine of x, so this becomes negative ln of cosine of x plus ln of u here is sine of y. Ln sine of y equals ln of c. Using the principles for logarithm, that is log of a minus log of b is equal to log of a over b. So this becomes ln of sine y over cosine of x because of the negative sign equals ln of c. We raise everything to e, raise everything to e, raise everything to e in order to cancel ln because e to the ln of x is equal to x, or any if a logarithm is raised to its base, okay, so it becomes one other principle for logarithm. If you raise a log of a number to its base, the answer is that number. Okay, it becomes that number. So this becomes sine y over cosine of x equals c. Ln cancels because we raise everything to e. So sine y over cosine of x equals c, or the final answer would be sine y equals c cosine of x. So we have now the solution for the general solution for the differential equation sine x sine y dx, sine x sine y dx plus cosine x cosine y dy equals 0, and that solution is sine y equals cos c cosine of x. Our third differential equation is xy cubed dx plus e to the x squared dy equals 0. As I've said before, we can simply separate the variables here, or we can transpose one term to the other side. In which case, after we have separated the variables and return it to the other side, the sign is still the same. So once again, we can have this transposed to the other side, or we can just operate with the 2 on the left side. So we'll try the two methods. We have xy cubed dx equals negative e to the x squared dy. Then we transpose all the x to be on the left side because we have our dx here. So we have x dx over e to the x squared equals, we have our dy here, our negative sign, and we transpose y cubed here. And then after we return it to the other side, we have positive dy over y cubed plus x dx over e to the x squared equals 0. In which case, if we do not transpose this expression to the other side and we simply separate the variables, that will also do it. It can yield the same answer. Like for example, we transpose y cube here, so this becomes x dx over e to the x squared plus dy over y cube equals 0. So as I've said before, you can transpose the other term to the other side, which would be the more the right thing to do. But then when you transpose it to the other side, you still get the same answer without having it transposed to the right side. So it depends whether you want to use this shortcut or you have to go through this detailed process. Okay, so we have now a differential equation with the variables already separated. So we integrate this and we integrate this. Okay. So here we have RU is equal to, here we can transpose e to the, we can have our exponent, we can have this whole expression in the numerator by changing its exponent to negative. So we have x e to the negative x squared dx. This is because in algebra there is in the laws of algebra we have x to the power of m is equal to 1 over x to the power of sorry, we have 1 over x to the power of m is equal to x to the power of negative m. This is one of the law in algebra. So, plus this is dy. We can also have our y cube in the numerator. Dy equals 0 before we integrate. Here we have a case of exponential integral of exponential function where our u is equal to negative x squared. Our du is therefore equal to negative 2x. And here we have x, but we do not have the constant negative 2. For which case, we can simply adjust the integrand by multiplying negative 2 here and multiplying negative 1/2 here. Okay, so we have negative 2x e to the negative x squared dx. And outside the integrand, we can have negative 1/2 so that it's just the same as multiplying by 1. Okay? So we adjust the integrand because we only differ by a constant from having our du. So this becomes integral of y to the negative 3 dy equals 0. We can now proceed with our integration. This is a case of exponential function e to the u. Our rule says the integral of e to the u du is equal to e to the u plus c. So we have e to the u and we have its du here. So we can proceed with this integration. We have e to the u plus c. We'll just copy negative 1/2 because it's outside the integrand. And the integral of e to the u du is equal to e to the u, which is negative x squared plus c. But we'll reserve plus c later on. Plus, this is a case of a simple power rule where we have y to the negative 3 plus 1 over negative 3 plus 1 equals c. Again, we can have c here, but then we can adjust this so that we can easily simplify our equation. But we'll first simplify this. So we have negative e to the negative x squared over 2 plus we have y to the power of negative 2 over 2 over negative 2. Okay? So, instead of just placing our c here, we can place here c over negative 2 so that negative 2 will easily cancel. So, I'll place here c over negative 2. And when we multiply everything by negative 2, we have e to the negative x squared plus y to the negative 2 equals c. Or, that is, we have e to the negative x squared, or 1 over e to the x squared plus 1 over y squared equals c. In which case, it's already our final answer because we can no longer simplify it. So this becomes our final answer. This can also be your final answer. However, I would prefer positive exponents in the final answer. With regards to the integral of x e to the negative x squared dx, I have adjusted the integral, the integrand in our previous solution by multiplying it with negative 2 and multiplying, placing a factor of negative 1/2 outside the integral sign. But I will show you the second way to solve it using substitution, which you might recall in your you have taken up in your integral calculus. So that is, we have a case of e to the u. So that is x e to the u dx, where our u is equal to negative x squared. If u is equal to negative x squared, then we have du equals negative 2x dx. We transpose negative 2x to the side where the du is, so that we have dx remaining on the other side. So we have du over 2x, negative 2x equals dx. And we substitute dx here, this one. We substitute here. So we have integral of x, here with the u. So we have now integral of x e to the u. Instead of placing dx, since this is equal to dx, this whole expression, we substitute it here. So du over negative 2x. Okay, so we cancel x, okay, and we factor out of the integrand negative 1 over negative 2, because it's in the denominator, integral of e to the u du. And if you recall in your integral calculus, the integral of e to the u du is e to the u. Okay, e to the u, or an exponential function, is unique, no, in differential calculus and in integral calculus, such that it is the only expression where its integral or its differential is equal to itself. So negative 1/2, we have e to the u plus c, or we have negative 1/2 e to the u is negative x squared plus c. So you see that we obtain the same answer using a different process.